So is this thing on? Yeah, all right. So we just finished up an example, or we kind of introduced this problem of a wood chipper driven by a electric motor, right? And we figured out that the stress on the tooth is something like 20 megapascals. But it just occurred to me, that was just the pinion. So what would the stress be on the other teeth? Well, wait. So the pinion engages the idler, and so if they're engaging, they must have the same module, and if they're engaging, they must have the same face width. So really, the stress on the pinion tooth should be the same as the stress on the idler tooth. And if we go around to the other side of the idler over here, now we've got the stress on the idler tooth should be the same as the stress on the gear tooth, right? Yeah, okay, so we're good. We're in good shape here. Yeah, all right, so we're good. I was kind of worried there for a second that we really screwed something up. But we did discover that it's only 20 megapascals, and I'm looking at hundreds of megapascals, so it seems like I maybe oversized my gear a little bit, or at least my pinion. I don't know. We'll find out. So the second pass at this, right, we're going to be a little bit more refined. We're going to use the AGMA method, American Gear Manufacturers Association. And this is a little bit different in that we're going to use, why did I switch colors there? We're going to do this J, which is the geometry factor, instead of the Lewis form factor, right, geometry factor. So let's take a look at that. Here, this is a little different. It depends both on, let's see, number of teeth N, and so that goes, we had 14. Maybe that's why I did it in red. So, and then it also matters number of teeth in the mating gear. So I'm going from 14 to 17, so I got to follow this line. Now I will go to red. I've got 17, so I'm going to go down this line here. Oh, but by the time I get down to here, it's all the same. So this is our spot here. And so I go over to here, and I'm going to guess that my geometry factor J is 0.24. Right. So I'm going to figure out a new bending stress, and that's going to depend on F tan, which I already know, M, which I already know, B, which I've estimated for first pass is 60, and now I've got J, which is 0.24. Right. So the units here still work out. All right, newtons per millimeter squared, and then J is some factor, and we've got some other factors. Okay, so we've got some other factors we're going to add on to this. So at least I've got one. All right, next up, stress. Second pass AGMA. Now we have to consider the velocity factor, and what the velocity factor is so as these gears come into contact with each other, they've got some, so here's the center, and these are gears, if you can imagine this. The faster they come at each other, the more kinetic energy they have, right, when they impact each other. One is driving the other, one might be going slower than the other, there might be some moment of inertia, or angular momentum, blah, blah, blah. So they have some impact, and the faster they're going, the faster that impact is, right? So that's really what the velocity factor is how hard are these teeth hitting when they first engage. All right. Actually, I gotta go back to the other the form factor first. So it says, let's see, on one axis we have pitch line velocity in feet per minute. Well, that's no good to us. Pitch line velocity in meters per second. Now remember that, let's see, go back to blue here. Velocity equals R omega, right? And so the pitch line velocity radius of, what was the radius of it? Is D 60, 70, I don't know, something. I don't remember what either one of those are, but I do know that the velocity worked out to be 9.1 meters per second. But you know what? I don't remember if that was for the pinion or the idler or the gear. So let's think about this. Okay, the pinion's going this fast, and let's say that's 9.1 meters per second. Well, what engages this tooth over here, if this is going 9.1 meters per second, so is this. And for that matter, so if the teeth here are going 9.1 meters per second, and now it engages the gear, those must also be going 9.1 meters per second. So this is really nice for me. The pitch line velocity of all three gears are the same. All right, so that's good. I was pretty worried about that for a second. So 9.1 meters per second. So we'll go back to the red guy here. And so we're looking at about here. And so I have to read over to my velocity factor. But holy cow. What is it? Hobbs form cutters, right? Hobbs shaping cutters, precision, high precision shaved in ground. Highest precision shaved in ground. I have no idea. I have absolutely no idea what I'm supposed to be using here. So this is from a different book, right? None of these books do a perfect job, right? But this one, Norton, Machine Component Design, I think this is a really good book. Except it's a little too heavily automotive based, in my opinion. But it's a good book. So Norton Machine Component Design says, here's kind of increasing quality, right? For whatever reason, the cement mixer is like the worst. I don't know why cement mixers get the worst. Maybe because they're always going to be coated in sand and concrete and you're going to have to replace them all the time. So don't even bother making them good. So that's the worst. The gyroscope, and we're talking about like the gyroscope that's used to stabilize aircraft and stuff like that. That is the best. Highest precision, shaved in ground, blah, 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 blah. And so increasing quality goes like this. And so what are we making? We're making a wood chipper. So I don't know where a wood chipper falls. Somewhere probably not as good as automotive transmission, but probably more around here somewhere. A wood chipper, This is the wood chipper kind of a range there, and so I've got to pick our velocity factor then based on this. So let's say this is the worst here, and then it gets a little better as we go down. So I'm going to say, I don't know, 2.4. Right? So let's just say, it's not the worst, but we're not going to put a lot of money into the gears on a wood chipper, right? They're not maintained well. They take a beating. So whatever, 2.4. So somewhere between, somewhere towards the worst end of cheap gears. All right. So now I've got K. The velocity factor equals 2.4, right? Heavily dependent on the quality. And we decided that automotive stuff, for your projects, you might be in the precision to high precision range. Wood chipper, pretty low. And if you're going to the cement business, I guess you get crappy gears. I don't know why that is. All right, so pitch line velocity. How did we get that? We talked about the fact that I've got my pinion, and then I've got a little bit bigger gear or idler, and then I've got my gear here that here my velocity here has to equal velocity here, so velocity here equals velocity there. So the pitch line velocities are the same everywhere. I forgot I put an extra slide in for that. We talked about this already. All right, next up is my overload factor, and this is why we're driving a wood chipper with an electric motor. Overload factor is kind of how predictable are my loads. So if I've got, I don't know, how about something like a gas turbine running a generator, right? Very smooth, high precision equipment here, constant angular velocity, constant angular momentum. Everything's really smooth and predictable, and driven by a gas turbine. Right, so thousands of blades, very, very consistent speed, very, very consistent torque. So that's the best I could do. A turbine driving a generator, very, very smooth. Whereas if I had, say, a wood chipper, where it's like sometimes there's a log in there, sometimes there's a nail that gets stuck in the log, or a branch, or a bigger branch, or somebody throws a brick, in with their brush. So it's very choppy. And if I drove that with something like a Harley Davidson, right? Potato, right? Really jerky kind of a driving force and a really jerky kind of a load. That means as these gears interact, holy cow, they're going to be slamming against each other all the time. Right? So let's take a look at the fact that we're driving an electric source of power. Electric motor, that's pretty good, right? But the driven machinery's got some heavy shock, so that works out to be a 1.75, right? 1.75. And I didn't even write that down. Yeah, okay. So 1.75. This is what we'll use for our overload factor, right? So keep in mind, these all multiply the stress, right? So I had whatever my 20 kilopascal or megapascals. I'm going to nearly double that just with that. What I'm going to do with this one back here, where to go? 2.4, right? That's going to be huge. So I've already doubled it, and I've almost doubled it again. There's something else I was going to say about velocity factor, number of teeth. Oh, yeah. I remember I was going to talk about something here too. So we've got load applied at highest point of single tooth contact. What does that mean? Or load applied at the tip of the tooth. All right, so let's talk about that for a little bit. And I don't have my nice gears with me. But as these teeth engage, right, they're going to engage somewhere in the middle. And then as it goes, then, the tip of this tooth is going to be engaged with the middle down here. So that's the worst case scenario, is when it's just the tip of this tooth that's carrying all the load, right? When they're back here, it's the, it's kind of middle. So we're not getting the maximum bending moment, right? So then you might say, well, down here, it is getting the maximum bending moment. But down here, there's also another, mating pair of teeth that are sharing some of this load. So that's why we have on here, whoop, that didn't work. Let's go back here. So the load applied at the highest point of single tooth contact, right? So when is only one pair of teeth carrying the load, and how high is the load? How close to the tip is it? That's this, right? So we get a little higher geometry factor. Higher geometry factor is good for us? Yeah, because it's in the denominator, right? So anyway, that's that. Velocity factor, we talked about that. Quality, cement mixtures. And then, cement mixtures, gyroscopes, that's good. And then this is why the pitch line velocity has to be the same everywhere. We discovered that if we drive, like if we drove a Harley Davidson driving a wood chipper, 2.25, more than double it. All right, and what's next? Oh yeah, the mounting factor. So, in this class, we're kind of neglecting deflections. And so when we neglect the deflections, right, we can just say, everything's perfectly aligned all the time. When the fact of the matter is this stuff is going to bend a little bit, which means the gears don't mate exactly the way they're supposed to. And so we have to account for that with the mounting factor. That's this one here, right? And so the longer the gears are, the longer the face width, the worse it's going to be. Right, because if it's a very short gear, very narrow gear, a slight misalignment won't be too bad, right? But the longer they are, the more accentuated these differences will be. So here again, I'm going to guess that a wood chipper. Right, I went with 2.2, right? And again, it's a little arbitrary. I don't know a lot of this yet, but ballpark 2.2. Is about as bad as it gets. All right, so that's that, and I think maybe we'll stop this video here. Now we can finally put this stuff in, but I'm going to do that in the next video. This one's already getting too long, so we'll pause.